Hey, Professor.
Yes.
Quick question. Will you be in your office hours today?
Yes. 4 to 5. Well, after this class for 30 minutes and then 4 to 5.
Okay, copy that. Thank you. Because I tried to join your office hours yesterday, but you might have been busy.
From 4 to 5 yesterday? What happened when you tried to log in?
Oh, it said, please wait for the host to start this meeting. I tried the office hour link, and I tried the main Zoom link just in case.
Really? I had another student tell me the same exact thing. I don't know. It's weird. I logged in from my phone, and I think maybe that may have been a problem. Not sure.
If you you know what? I think that happened to me one time. If you have a personal meeting ID that you use and it's not turned on, I think it starts its own meeting ID, and it's different from the one on the website.
Yeah, well, I was in a place where I wasn't able, I unfortunately had to go help a friend who's had a vehicle trouble, but I wouldn't be able to do much on screen anyway, but I'll be there today.
Okay, thank you.
In the future, if that happens, just text me or call me.
Okay.
Okay.
Thank you.
All right, everyone. Welcome back. Today, what are we doing? Today we are getting into the Cal 2, talking about antiderivatives. For my former Cal 1 students, we still have the next 2 sections I did in Cal 1, so it's still stuff you've seen. It'll start to feel new once we get to 6.1, which will be right after 5.5. All right, so here we go. We're going to do antiderivatives today. Next week, we're going to do substitution. And the handwritten homework for 3.6 and 4.7 is due this Sunday at 11:59 p.m. I looked at what you submitted for the 3.5 homework, and for the most part, I was pleased. I just glanced over everyone's, and I gave everyone a grade. I made any comments about your submission if I felt like there was something I should mention to you. So, I gave you some feedback. I'll try and do that for each of the assignments you turn in. Any questions before I begin? We're ready to roll. Okay, let's get into to today's material, antiderivatives. So I think what would be good is if we first talk about, what the main kind of concept here is. In Cal 1, what we did was we started out with a function, right? Some function f, and we did this thing called differentiation, right? We took the derivative. And when we took the derivative, it gave us a new function, right? A completely new function. And that new function, since it was a function, has its own graph. Like we can actually take a function, take its derivative, and graph its derivative. So we have some other function over here. Let's say it's not going to be exactly right, but there we go. That's, let's say, the derivative of this original function f. And we did that for all these different functions, right? We learned all these rules, and power rule and product rule, quotient rule, chain rule. And then we've got all these exponential log trig functions. Now we've got the inverse trig functions, hyperbolic functions, inverse hyperbolic functions, all these things we can take derivatives of. That's pretty much what Cal 1 is about. And then, of course, you do things with it, right? You do things. You have applications. So what Cal 2 is about, at least the beginning of this class, is going to be, we want to be able to go backwards. So we want to be able to find, what will be referred to as the antiderivative. So if we start with a function, and I don't want you to think about this function anymore as being the derivative of something. I just want you to think of, oh, what if we start with some function and we go backwards to the antiderivative of that function? We will call the antiderivative of that function, we will notate it with a capital F. All right, so we're going to start here now. and then go backwards and end over here. All right. And that's the first kind of 1/3 of this class, is us getting good at that. And then we'll see why. Okay, so the why is going to come later as to, you know, what's the usefulness of this. It's just about let's get good at doing it first. All right. So now let's get to the actual definitions and stuff. So the notes here again are online for you. I'm going to breeze through these. There's only 5 notes for this section, so we're going to really do a lot of exercises today, a lot of examples. So first we have to start out with like the formal definition. A function capital F, okay, is called an antiderivative of little f. So see how I'm saying that? Capital F, little f, on some interval I, if the derivative of capital F is equal to little f. So that goes back to this picture. If we take some function little f, we start here, then we will call this function the antiderivative of little f, as long as when we take the derivative of this, we get back that. Okay. Now, in that definition, there is one word in here, capital F, is called an antiderivative. Not the antiderivative, it's called an antiderivative. And that has some implications, that word. It has the implication that maybe there's more than one, right? Like this somehow is saying that a function f, capital F, is called an antiderivative little f. In some way subtly says, well, maybe there could be, you know, 2 antiderivatives of a function or 3 antiderivatives of a function. So let's investigate that. All right. And to do that, let's just start with an example. Let's say I give you a little function here, capital F of x equals, let's go with 3x squared. Okay. Little f. And what I want you to do is find capital F of x. In other words, I'm asking you to I.E find an antiderivative of that little f guy. All right, so I'm going to call on people because I'm not sure what your background is on this. And let me switch to this class here. Who did I not call on last time? Adalissa, is that right? Am I saying that right? Adalissa? Adalissa Rosales? No. Okay. How about Joyce?
Weird question.
I'm sorry?
I kind of have a strange question.
Okay.
Well, since you can, because if you have a derivative of a function that you're starting with, and you can use that to eventually find the antiderivative gets you the original function, is that correct?
The antiderivative is any function you can come up with that when you take the derivative of it, you get this answer. I'm not sure if that's what you're asking.
So if I have, what I'm asking is if I have a derivative of a function and I try to find the antiderivative of that derivative, will it get me the initial function?
Yes.
That was used. Okay.
Yes.
So
go ahead.
In this case, because what you have on screen is not a derivative but a regular function, it looks like you can take the antiderivative of a traditional function as well. It's not a derivative, right?
Yeah. So here's the way I think you should look at it, Joshua. When you starting out in Cal 1, you started with a function, right? And you took its derivative. You took its derivative. Well, that derivative itself is just a function, right?
Yeah.
The derivative is a function. So just act like we're not even calling it a derivative of something anymore. We're just saying, let's start with that function and let's just call it f. Now go try and find me the function that when you take the derivative of it, you get back this function. Yeah, so it's We're not labeling this anymore as the derivative of something. We're just calling it the F. Now, the notation is that its antiderivative will be called capital F. So the capital and the lowercase are what help us understand the relationship between the two functions.
Okay, I got you. Well, and because when you take the derivative of a function, it usually helps you find things like the rate of change, right?
That's right. Yep.
Okay, so if you take the antiderivative of a normal function, what would be what would you be able to determine from that as
Okay,
opposed to the
so
rate of change?
that's tied into the thing that I said here. Like what we're going to focus on right now is doing it. And then after we get good at doing it, we'll talk about what it's useful for. Okay. Now
Okay.
I will give you an example today of what it's useful for. I will give you an example today, just not yet. I will try and assign some sort of meaning to it today. I don't want to just keep on doing it without having any sense of why we're doing it, but just hang tight on that. Let's get the mechanics down first, get the terminology down, and then we'll actually talk about how we can use it for something.
Okay.
That's a good question.
Thank you.
If the derivative is a rate of change, then what is the antiderivative, right? Some sort of reverse of the rate of change. So we'll discuss it. Okay, was Joyce here? No, Joyce? Do I have the right class? I think I'm in the right class here. 2414, yeah, so no Joyce. Okay, how about Jonathan? Yep, I see you there. Okay. So Jonathan, what I'm asking you for is, can you think of any function, capital F, that when you take the derivative of it, you get this 3x squared?
Yes, it would be x cubed and then
Okay,
plus
x
a
cubed.
constant.
Okay, yeah, so you've obviously done this before.
Mhm.
X cubed would work though, right? Does everyone agree that is an answer? If I take the derivative of that, I get 3x squared. But like Jonathan said, there's something else. So Jonathan, before you get to that, because I haven't talked about that yet, give me another example.
X cubed plus 1.
Plus 1. Okay, good. That would work also, because when you take the derivative of x cubed, you get 3x squared, but when you take derivative of 1, you get 0, right? And Jonathan, give me another one.
X cubed plus 10.
Plus 10, right? And Jonathan could keep going forever here, right? Just keep on adding numbers to the outside of that, and all of these would qualify as being antiderivatives. I could do capital F of x equals x cubed. We don't have to do a plus, we can do -4, let's say, right? So all of these together, these are all antiderivatives. Those are all antiderivatives. So if we start with some function like 3x squared and I ask you for an antiderivative, you only have to give me one of those answers and it would be correct, right? Any one of those would be a correct answer. But there are an infinite number of them, right? There's an infinite number of antiderivatives, right? There's an infinite number of them because we can add or subtract any number from them. Now, having an infinite number of answers makes you think, well, wait a minute, there's an infinite number of them, so how is this ever going to be useful? Well, the thing is, all of these functions have something in common, all right? They all have some similarity to them. If you were to graph them, they would all have some property that makes them somehow connected to that 3x squared. So if I graph x cubed, there's x cubed. If I do x cubed plus 1, there's that one. If I do x cubed plus 4, there's that one, right? X cubed, let's go -10, there's that one, right? That one's way down here, okay? They all have something similar. If I do this, x cubed plus any number, I'm going to say c, and then this software allows me to add a slider to the c. I can adjust the value of c, move it up and down, and any of these functions would qualify as an antiderivative, right? Any of them. So imagine all of them, right? They're all there, all infinitely many of them. They all are in what we call a family because they all have something in common. I'm going to zoom in so you can see it. The similarity they all have is this. if you pick any value of x, okay, let's go pick some value of x, and then go to the functions on that point. Okay, right there. Let's just look at these, okay? What do all of these functions have in common at that point? It's not their y values, right? It's not how high up and down they are, but there's something else that they all have that's similar. What is it? I see Lewis.
The max
The
value.
slope, right? If you were to take the slope of the tangent line, that slope is equal to that slope, is equal to that slope, is equal to that slope on any of the members of the family, right? And that would work for any of the function, or anywhere I go on the function, I would have that. If I went over here, well, let me go here. If I went here to look at these points, all of those points would all have the same slope. And that's what it means to say that capital F, when we take its derivative, is equal to little f, is basically saying that for any member of the family, right, any of these functions in this family, if I take the derivative, the slope of the tangent line is going to be the same for all of them at that point. Does this make sense? Any questions? Okay. So we have capital F. Capital F is the antiderivative, or is an antiderivative. So now let's continue. If capital F is an antiderivative of little f, then capital F of x plus c is the most general antiderivative of little f. So if I ask you for an antiderivative, you can give me any member of the family, right? Any member you want, you give it to me. But if I ask you for the general antiderivative, all you're going to do is give me any capital F and add a constant to it. And you'll use capital C for that constant. That's the common notation we use, okay? So let's do another one. I see a lot of you understand this because I know a lot of you have seen this in Cal 1. So let me give you a different example. Let's say we have little f is equal to, let's go with, yeah, let's not be too mean right now. Let's go with 1 over x minus 2x plus 7. Okay, and I want you to find the general antiderivative. All right. So let's go to Lauren. Is Lauren here?
Yes.
Yes, you are here.
I'm here.
I'm looking for you. I don't see you. Oh, there you are. Okay. All right, Lauren. Did you do antiderivatives in Cal 1? A little bit? No?
Yes, a little bit.
Yes. Okay. So my question to you, Lauren, is this. In Cal 1, when you took derivatives, right? Derivatives, not antiderivatives. When you took derivatives, if you had 3 terms, when you took the derivative, you did a derivative of each one separately, right? If you have addition, subtraction, you could do derivatives separately, correct, Lauren?
Yes.
Okay, so antiderivatives work exactly the same way. Because we have addition and subtraction, you can, instead of trying to look at the whole thing, anywhere you have addition and subtraction, you can just try and find me the antiderivative of each one of those. All right. So let's see if we can get that. Lauren, for those 3, can you tell me the antiderivative of any, you pick any of these 3. Can you tell me the antiderivative of any one of them?
The second one is x squared. Or negative
X squared. Okay, so for the 2x, this would become x squared, and I have the minus still there, so minus. Is that what you meant?
Yes.
Yes, okay, good. I want to get through people today, so Alexander, you're up.
The 1 divided by x, that'd be I think the harder one. Wouldn't that be x? Because it would be,
So in Cal 1, what
Yeah,
did you take the derivative of and get 1 over x?
It'd be natural.
Oh, hold on.
Oh, I'm sorry.
It's all right.
Oh, well,
Right.
it was spoiled. Yeah, natural log of
Right.
x.
Natural. Did that ring a bell now? Yes.
Yeah,
Natural
now it
log?
does. I was stuck on like the x to the power of
You were
negative
trying to
one.
think of a power, right?
Yeah,
So
that's
the
why I
1
was
over
stuck.
x is the special one. We just need to kind of remember it, right? Like that's a
Yeah.
really special one. Okay, but you went for the harder one. I don't know.
Yeah.
Some would argue that the last one's the harder one. How about Caitlin? How about the last one, Caitlin?
The last one will be 7x.
7x, good. So does everyone agree that what I just put up here is an antiderivative? It is an antiderivative, but it's not the general one, right? The general one, all I have to do is just slap on the plus c. And now I have the general antiderivative of that. Good. Good. All right. Now, when it comes to doing antiderivatives, we start to see patterns in how to find the antiderivative if the function we're given is something special. So let me give you this example. If we have f of x, like let's do this one. Let's go with x squared, right? If we want to find the general antiderivative, we know, Ricardo, right? What do we know from Cal 1? What is the power of this answer going to have to be? If it's the antiderivative of x squared, what is the power on the x going to have to be?
So you'd subtract 1, so it'd be a 1.
That's if you're taking the derivative.
Oh, yes, I'm sorry.
So we're going backwards.
You'd add a 1, yeah.
You'd add 1, exactly. So whatever the antiderivative is, right, this x, we know that this power has to be 1 more than the power there. So we know that that has to be x cubed, so that, you know, when we take derivative, we subtract 1 and it would become x squared. But because of the power rule, this 3 would also come out, wouldn't it, when we took the derivative? And we don't have a 3 out here. So Ricardo, what would we need out here that would somehow like kill that 3 off when it comes out?
1 over 3.
1 over 3. And now hopefully your comfort level with Cal 1, you feel like, okay, yeah, if I took derivative of this, 3 would come out, it would cancel with the 1/3, I get x squared, I'd be done. Tack a plus c on, right? Let's do a quick poll. I mean, I'm assuming just by the look of you, y'all get it. How many of y'all are comfortable with that idea, what I just did there? Okay, good. Let's keep going. So what we develop from this idea that Ricardo was just saying, if we ever have a power here, we always know that that's going to be adding 1 to the power, right? So if we try and generalize this and come up with a formula, we know that if we start with x to a power n, we know that the antiderivative would have to have that power n, but we would have to add 1 to it, right? But then again, because of the power rule, when we took the derivative of this entire n plus 1 power would come out front, right? It would drop out in front. And we don't want it there because there's really a 1 out here in front of this one. So to kill it, what we would put out here is a scalar. We would put the scalar 1 over n plus 1. And just remember, this right here is just going to be a number, right? So we're putting some number in front of our power. And that way, when this number comes out, this kills it off, becomes a 1, and then the power will come down by 1 and become the n. All we have to do is throw a c on it, and we're in business. So this right here is actually a formula that we use for antiderivatives, and this is called the power rule for antiderivatives. This power rule is very useful, okay, especially when we start getting complicated powers on the x. But there is one value of n where it doesn't work. There is one particular power I cannot use this formula for. What power is it? What power on n will this not work for?
Was it
-1?
-1?
-1. If n is -1. Now, why wouldn't that work? If we had n being -1, what would happen if you try and plug -1 in right here?
Because it'll make it a 0.
The x over
You'll have a 0 and it'll be division by 0 and it doesn't work, right? So this formula actually breaks down if n is -1. So I need to add something to this. I need to say that, you know, this is true if n is not -1. So this rule only works if n is not -1. So that means we need to now look at what if it is, right? So what if n is -1, then what is the original function we're looking at? The original function, if I replace that x with -1, it would be, or the n with -1, it'd be x to -1, wouldn't it? What I'm saying is our formula doesn't work for this, right? Our formula does not work for this. But if we just recognize this is just 1 over x, right? That's all that is. X to -1 is 1 over x. Then Alexander and Brandon already talked about this earlier when we were doing this example right here, the antiderivative 1 over x. We have to remember that from Cal 1, right? That is capital F of x here would be the natural log of x plus c. Now there is something here I did not say when we did this, but I'm going to point it out now. When we're doing antiderivatives of this very special function 1 over x, we always put an absolute value around the x. And that is because we need to have a domain restriction, because we can't plug negative numbers into a natural log. So back here, we would want an absolute value around this x here. So everything I have in like boxed up right here, along with this, that's pretty much a rule to find the antiderivative of x to any power, right? So from here on out, if I give you a function where it's x to a power, we have a very, very clean, easy formula to use. So let's just make sure you're comfortable with that by doing an example. Let's say f of x is equal to square root of x minus cube root of x plus 1 over the square root of x minus 1 over the cube root of x. I want us to find capital F. And when I say capital F from here on out, I'm talking about the general antiderivative. Okay, so I want you to put the plus c at the end. All right. So first things first, let's see, Joshua, you there? Yeah, you are there. So Joshua, you see that we have 1, 2, 3, 4 of these terms, and we can do them one by one, right?
Right.
We can antiderivative each one. And
Well, oh, go ahead.
no, you go. You said you were going to say the first something. I don't know what you're going to say.
Oh, okay. Well, what you used was it was 1 over n plus 1 times x, then it was x or n plus 1. So if you've got 1/2 x to the first half power, you can do
Okay, hold on,
1
Aaron. Or Joshua, let me ask you something. Can we first just rewrite all of these before we find the antiderivative? Because you said x to the half. I want to make sure everyone's on board. We're just going to rewrite
Yeah.
the square root of x is x to the half. And then let's rewrite all of these, and then we'll go do the antiderivative.
Okay.
So this is x to the half. What's the next one?
You've got x to a third.
Okay.
X to -1 over a third.
Good.
And that
So you
works
rewrote
because
the bottom
it's
as
only
x
a
to the
negative
half,
1.
brought it up. Yep.
Or a half, yes, I'm sorry.
No, you said it right. So
Um,
you rewrote this as x to the half, then you brought it up x to the -1/2. You rewrote this as x to the 1/3, and then brought it up as x to the -1/3.
Yeah, and then you just apply the formula to each one to find your antiderivative.
That's right. All right, that's what we're going to do. We're just going to apply the formula. So we have 4 different problems now. We have 4 different ends. 4 different ends to do here. So take a minute, crank it out, clean it up, and I'll call on a volunteer in a minute to get an answer. Please do the poll. Let me know when you're done. Okay. I just want to see how long it takes y'all to get through this. So when you're done with all of those, put them together. Tell me yes.
Oh, we're done.
So far, we have 8 people done out of 17, out of 16. 17, sorry. Got 11 of you done? 12 now, 13? Okay, good. We're all done with that. Were there any questions over that? Everyone said they got it. Nobody has any issues with this? The thing that I think you have to get good with in this power rule is just adding 1 to a fraction. Like if you can get that down and do it, faster and faster each time, then this becomes, pretty quick. Some of you all are done in like the first minute. So I can tell you've done this before. Okay. We're good? No questions? No questions? Give me another one. Okay. Let's talk about this one. All right, let's do a poll. Okay, I want to just ask you, do you feel like you know how to go about this? Do you feel like you know what you need to do right now to find the antiderivative? Okay, good, good. All right, so about 2/3 of you, no, 70% of you are a little confused about how to proceed from here. So what if I didn't have all that down there? Then you could do it, right? That's basically like the previous problem. Agreed? Yes, just shake your head. Yes. Yes. Okay, so it's this division thing that's causing an issue. Now, let me show you what you cannot do. All right, what you cannot do is say, oh, I'm just going to find the antiderivative of this, antiderivative of this, antiderivative of this, antiderivative of this separately. You cannot do that. All right, like we did it here, right? We just did each one separately, but that's because we had 4 terms separated by addition and subtraction, so we're allowed to do that. But here we have a quotient, right? We have division. And when you do, back in Cal 1, when you took a derivative and you had a quotient, there was a whole rule for it, right? Right, in Cal 1, I know you know this, but I'm just gonna put it down here just to be clear. In Cal 1, if I gave you this function, x squared over sine x, and I ask you to take the derivative, right? You would not do this, right? Or else you would go to math hell, right? You would not do that. That's just taking the derivative of the top and bottom separately, which is not the way you take derivatives of quotients, right? You can't do that in Cal 1. There's a whole rule for it. So this is no good. So if we're doing an antiderivative and we have a quotient like this, you can't just do the top and bottom separately either, right? I mean, it won't work that way. So here's what I want you to see now. Now, okay, some of you said you knew how to do it. So does someone that knows how to do it want to share how they're going to do it?
You can move the root up.
You can move the root up. So I think what you mean by that is you're going to rewrite 3x minus 4 root x plus x cubed. And then you're algebraically going to move this root, which is really x to the 4th power, right? That's
Yeah,
what that is.
Negative 1/4 on the top.
And bring it up as an x to the negative 1/4. And then that would have to multiply through, wouldn't it? Like it would have to distribute through here. So this is all algebra. Does everyone agree that Ricardo's suggestion here would be like a legal algebraic move?
Looks good to me.
Okay, let's do that. So now you have to distribute this through here, here, and here. So I'm just going to write it down. We're going to do 3x and we're going to multiply times x to the negative 1/4. Then we're going to do minus 4. I'm going to rewrite that square root of x as x to the half. We're going to multiply that by x to the negative 1/4. And then we're going to add to that x to the 3rd times x to the negative 1/4. Again, this is just algebra. We're still dealing with f, right? We have not done the antiderivative yet. All we're doing is manipulating f, massaging it, making it look different, and then we're going to try the antiderivative. So continue to combine these together. And I'm just going to state this one time. When we multiply x to the 1st power times x to the negative 1/4, we are going to add those powers together, right? So it's 1 plus negative 1/4, which is same as 1 minus a 4th, which is 3/4. Okay, so I don't want to have to do that for each one of these, but that's what I'm doing. X to the 3/4 minus 4x to the, what's that? What's a half take away a 4th?
A 4th.
It's a 4th. Okay, so you got to be comfortable doing that. But you're Cal 2 students, right? You know how to add and subtract fractions. All right, plus,
We learned it.
I say that almost sarcastically because I realize, like, you know, everything is delayed, right? When you get to Cal 2, that's when you get really good at derivatives, right? When you're in Cal 1, that's when you finally get decent at algebra. Like, there's always a delay for things. So when I say, oh, of course, you're a Cal 2 student, you can do fractions, I realize that maybe you're not like a fraction machine yet, but you're going to have to become one, right? As time goes on. What's this last one? X to what power?
To the 3rd.
What was it?
Cubed.
X. I'm putting these two together. What is it?
Yes. It's x cubed. Oh, you would do 12 over 4 minus 1/4,
12 over 4 minus 1/4, which is
11/4.
11/4. Good. So 11/4. Plus C? Plus C? I see yeses and nos.
No,
I haven't taken an antiderivative yet, right? I haven't done any antiderivative yet. All I've done is clean,
Oh,
is like manipulated it. So this is just what f of x is. Now the antiderivative, right? So now comes my antiderivative. Hey, what do I do with all these constants? This for, what do we do with those? Because we have a formula that deals when we have just the x to a power, right? But what about the constants that are in front here, like that 3 and -4? What can I do with those?
Can we just move them all the way to the front?
Yeah, just keep them out in front. Like use the formula on the green part. Okay, so use your formula for this and just tack the 3 onto the front. So 3 times, and now use your power rule on this, which would be your 1 over n plus 1 x to the n plus 1 minus, then bring your 4 down and then do times 1 over 1/4 plus 1 x to the 1/4 plus 1, and then plus 1 over 11/4 plus 1 x to the 11/4 plus 1 plus c. Now the plus c.
Correct me if I'm wrong, sir. I feel like, isn't there an easier way to do this or no?
There's a different way to do it. I'm not quite sure I'd say easier.
With the
We
whole
can
like,
talk about that. We can talk about, let's finish this off and then we'll
Okay.
talk about maybe another way. Fair?
yes, sir.
Okay, so I'm gonna keep going here. This is 3 times, okay, let's figure out what this is. 3/4 plus 1, 7/4, right? And then 1 divided by 7/4 is 4/7. And then x to the 4/7, no, yeah. 7/4. Minus 4 times, okay, 1/4 plus 1, that's 5/4. 1 over 5/4 is 4/5. X to the 5/4. Plus 11/4 plus 1 is 15/4.
should be.
And then 1 over that is 4 over 15. X to the 15 over 4. And then plus c. One more thing before I box this up, I'm actually going to multiply these together. So I treat that as a 3 over 1 and just multiply across the top. So 12 over 7, x to the 7 over 4. Minus, I multiply across the top there again, 16 over 5, x to the 5 over 4, plus 4 over 15, x to the 15 over 4, plus c. There we go. There's your general antiderivative. I'm getting the sense that a lot of you did this in Cal 1, which is very good. I'm glad. All right. Now, Mohammed asked about perhaps an easier way. Did you have a suggestion, or were you asking me just because you feel like there's an easier way?
No, it's I feel, well, I think I've seen it in Cal 2, but I don't remember it because, or no, sorry, not Cal 2, Cal 1. And it was like in the spring, so it wasn't spring, it was in the summer, but I don't remember it. It was something to do with like taking the derivative of the top, multiplying it by the bottom or something like that. I don't remember.
Maybe you might be confusing actually like taking the derivative of this,
Okay.
which would be the quotient rule, which is what you just described. Like you take derivative of the top and multiply times the bottom, then you subtract the derivative of the bottom times the top, and then put it all over the bottom squared. That's the derivative of this,
Okay.
but that's not the antiderivative. The antiderivative is we're trying to reverse it, go back.
Yeah.
One thing, the way that I would have done this, and this is just me, this is not wrong, the way it was suggested we do it. If it were me, I would just do this. I would first just switch it all over. Okay, all my radicals I put in as rational exponents. And then instead of bringing that x to the 1/4 up, I would break this into 3 fractions. I would go this over this. And then I do this over this. And then this over this, like that. And then I would use the same sort of properties of exponents. When I have x to the first power over x to the 1/4, I subtract the powers. So 1 minus a fourth is 3/4, so x to the 3/4 minus 4. And then I do the same thing here. I do 1/2, I take away a fourth, which is x to the 4th. And then on the last one, I would do 3 take away a fourth, which would be x to the 11/4, which is exactly the same as that right there, right? So I'd still need to take the antiderivative, but it's just another way of simplifying the expression. Okay? All right, I have another one for you. Let's see if I have it in my notes. Yeah. 2 plus x squared over 1 plus x squared, yeah. All right, so I'm kind of this is a little bit of a challenge, this problem. All right, I'm just gonna let you look at it for 2 minutes. 2 minutes. If you get it, I want you to tell me you got it by answering the poll. And I don't mean go type it into like Symbol Lab. I mean, you got it. So we're a minute in, and I have one person who claims they've got it so far. 2 people claim they have it. Louis, I got your chat. Thank you. Okay, I think that's enough time. So look, what is like inherently different in this one? Miyaki here?
Yes.
Okay, I say that okay?
Yeah.
Okay, good. So did you get it or no?
No.
There was
no.
2 people said they got it. Okay. So Miyaki, what is kind of different from this one and the one before? Like what's like, do you see what's like kind of inherently different? between the two?
The denominator has we added the x squared. So
Exactly.
I think
We
that
have
makes it a
2
little
terms.
harder.
Yeah, we have 2 terms in the bottom. So you can't do what we did last time where we just brought that up. Like Ricardo had said, hey, take that x, the 4th root of x, and let's bring it up as an x to the -4. You can't do that because it's not just x squared here. If it was just x squared, yeah, you could either split it into two terms, or you could bring the x squared up as an x to -2 and distribute it. You do it exactly the way we did the previous one. But it's that 1 plus that's causing an issue. All right. So how do we go about this? Well, two people said they got it. One of them said they'd seen it worked, which means someone else maybe got it on their own. I don't know.
I just said this is, or I'm taking okay, I cheated. I looked at my notes from previous class.
Okay. All right. We won't count that then.
Okay.
We won't count that. All right. So here's the idea here. And this is kind of like our first glimpse into what Cal 2 is about. See, the power rule that we just got is great if you've got x to a power, right? And it's by itself, it's its own term, great. We can find the antiderivative, no trouble. But when it comes to formulas like that, that's about all we ever get in Cal 2. Like we never get like an equivalent, like, you know how we had the product rule in Cal 1? We don't get something in Cal 2 called the product rule for antiderivatives, or the quotient rule for antiderivatives, or the chain rule for antiderivatives. We are constantly trying to find a way to like reverse this, and it's just really hard. Okay, it's just really hard to do in general. And this problem is kind of your first kind of glimpse into it. All right. So there are two ways to go about this problem. They're kind of two approaches. I'm going to show you both. One of them is this, and would you ever think of this? Who knows? One of them is this, is to realize that you could rewrite the 2 as 1 plus 1 plus x squared over 1 plus x squared. Okay. Now, if you do that, which no one would, no like normal human being would do that, right? If you do it though, what you can do is you can kind of say, you know, now I'm going to split it into two pieces. I have this 1 over the denominator plus, because that's a plus right here, this whole thing over the denominator. But wait a minute. This over the, that's the same thing, right? That's the same exact thing. So this is really 1 over 1 plus x squared plus 1. That's what this function little f is. Do y'all agree with that? And that was by me doing something weird, just splitting that 2 up into 1 plus 1, very unnaturally. Now, when you look at this, now you can focus your attention on each of these individually because you have a plus sign. I hope we're all comfortable with the idea that the antiderivative of 1 would be
X.
x. Okay, so x. I will have a plus c out here. The only thing left for us to figure out is, do we know the antiderivative of this?
It's arctangent.
It's arctangent. How do you know that? Well, because you were here a few days ago when we were talking about derivatives of the inverse trig functions, and somewhere in our notes, somewhere, I don't know, right here, right there, we talked about what is the derivative of arctangent, and I said it was 1 over 1 plus x squared, and I put 2 stars next to it, and I told you this is going to come up a lot in this class, and to be ready for it. And so now here's the first time we're seeing it. We want to know the antiderivative of this, which means we need to know where it came from, and it came from arctangent. All right. So I just put here inverse tangent of x plus x, because that was a plus here. And then there you go. That's it. Okay.
That's a weird
Yeah.
one.
Yeah. So how would you, how would you have come up with this? Well, now you've kind of seen it. Like now you've seen it, right? So now you've got that kind of planted in your brain. Like, okay, you look at it now, and maybe in retrospect, you say, look, that 2 there, it'd be really nice if it were a 1, because then it would just be the same damn expression. So maybe I just rewrite it as 1 plus 1 and just see where it goes, right?
So I had a question, because I
Yeah.
did see the 1 plus x squared on the bottom, and I thought to myself, this is going to end up with arctangent.
Good, good.
Is there a way, another way, like a traditional way, I guess, not.
I have a little bit more of a traditional way of doing it, a little bit.
Okay.
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 Here's the
I didn't
second.
think of the whole 1+1 thing, so
Yeah.
I was thinking to myself, how do I separate them? I had no
Yep.
idea.
So here we go. Here's how we would do it. The other way, which I guess is a little bit more natural than seeing the 1+1, is to look at this fraction and go back to college algebra and do long division. So take the numerator, rewrite it in descending order, x squared plus 2. So remember when we do long division, we take this polynomial, write it in descending order. Notice I left a gap here because we don't have an x term, so I'm just going to put like 0x. And then on the outside, you put the divisor. The divisor here is the denominator, x squared plus 1. And now you play your little game of long division, which is to try and turn x squared into x squared. So you have to multiply by 1. So I put a 1 up here. Then I multiply 1 times each of these. So when I do 1 times this, I get x squared. When you do 1 times this, you get 1, you put it underneath the 2. You come through and you subtract this row. The x squareds cancel. You don't have anything here. 2 minus 1 is 1. And then you continue with your long division, which is to try and turn x squared into 1 now. But you can't because x squared has a higher power than 1, so we're done. So what we put up here is plus the remainder over the divisor. So if you need to go back and review long division, go review it. That's the way it's done. This right here is that line. That makes sense? So maybe this is
I have a
the first.
question.
Yeah, go ahead. Question?
Would synthetic division also be, could we use that as well in this case?
Good question.
long
Can
division?
you? Are you saying, can you use synthetic division like in general, or are you saying, can you use synthetic division for this problem?
For this problem?
Okay, let me ask you, can you?
I'm
What
not
do y'all
sure.
think? Can we use synthetic division for this?
My memory is correct. Can't you use synthetic division wherever you can use long division?
Okay. Can you use synthetic division in place of long division all the time?
I don't think so. It's
Last
not going
time-
to give us the same answer or what we're looking for.
Okay, so let's do just a real quick recap on this. When you were in college algebra, and I know it's been a long time, you're taught synthetic and you're taught long division, right? Synthetic is quick, it's nice, boom, 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 you do, yeah, right? I mean, it's a real nice little method. Long division, well, it's long, it sucks, you got to keep track of a bunch of stuff. So if synthetic could always be done in place of long, then we would never teach long because you just always use synthetic. The deal with synthetic is this. To do synthetic, you must have a polynomial being divided by a linear expression. It has to be linear on the bottom. Then you can use synthetic. Long division works for any polynomial divided by any polynomial. So the degree over here of the numerator and denominator doesn't matter, okay? Does not matter. Here, for synthetic, the numerator's power really doesn't matter, but the denominator has to be x to the first power. So like you could do this, x squared plus x over x plus 1. Yes, synthetic for this. 1, 1, 0, -1 out here, 1, -1, 0, 0, 0. Okay, so that looked kind of familiar. I'm going really fast. That can be done with synthetic. But, and if you did that with long, it would look like this. And then out here, x plus 1, and then you do your long division, right? For the problem that we're working on right now, we could not use synthetic because the denominator is not linear. So we have to use long. Good question. Good question. Okay. So in this problem that we just did, everybody had to recognize that 1 over 1 plus x squared, you had to recognize that that's the derivative of inverse tangent, right? So that means now anything that we can remember from Cal 1 is fair game in terms of finding antiderivatives. It means all those things that you know about derivatives now are on the table in terms of like the common stuff. So in the notes, I remind you of all of the things that you actually kind of know, right? If you go back to Cal 1, you know that the derivative, right? If we take the derivative of this, we get secant squared, right? So if you ever see secant squared and you want to find its antiderivative, you better know that the antiderivative is tangent. In Cal 1, we know the derivative of secant is secant x tangent x. So if we ever see this, we need to know that the antiderivative was secant x. And this goes for all the things we just studied, right? The hyperbolics that we just studied and everything we studied. This right here on this side is more Cal 1. 1 over x, we need to remember natural log is the antiderivative. E to the x, antiderivative is itself, e to the x. Antiderivative cosine is sine. Antiderivative sine, negative cosine. So it's this direction is the anti, right? That's what we're saying. So I just spent like a minute and a half explaining to you that everything that you know in Cal 1, you better now know and recognize, okay? So it's a small statement, but it encompasses a lot of stuff, all right? One good way to kind of go back and look at this and review it and kind of be like, what should I know? Is if you go to our formula sheet and you go to the first, there's this first page, reference 6. It's called Table of Integrals. Now, for right now, ignore that integrals, we haven't talked about it, and ignore this weird notation here. I want you to just pay attention to, if you look at this right here, the antiderivative of e to the u is e to the u plus c. This formula sheet gives you a bunch of antiderivatives. So here's like sine and cosine and secant squared. Now, if this is hard to read at this point, you can always go back to this page, these pages where these are the derivatives, and you can kind of remind yourself like this one right here. That's the one we just used, right? We saw this in our formula, and so we knew that it came from taking the derivative of that. You can use these formula sheets on the test, okay? I have no problem with you using them, but there are certain things you should just like recognize, all right? Like, oh yeah, obviously the antiderivative of, let me get to this. So like if I give you, f of x equals cosine of x, like you should just be able to go, oh yeah, well, of course, I know that when you take the derivative of sine, you get cosine, so it should just be sine x plus c, right? So there's a lot of stuff now that's kind of on the table. Question? No? All right, 12:03, let's keep grinding away here. The next topic today is to look kind of with what Joshua asked at the beginning, like if taking the derivative is the instantaneous rate of change, then what is the antiderivative giving us? I want to use that kind of as a launching point for the next topic. So let's see if you remember this. Hopefully you were taught this in Cal 1. Let's say you're given a function. Let's call it, let me make sure I have, I want to follow the notes I have. S equals f of t, all right. So let's say you're given some function, we're going to call it s and it's some function of the variable t. So usually we use f of x. I'm going to use f of t. So t is our variable. T here is going to represent time. That's why I'm using t instead of x. And s, which is this function, I'm going to tell you is a position function. In other words, if you give me a value of t, this function will spit out the distance that some object has traveled. All right. So if I were to look at this graphically, this is t, this is the s. Let's say at time is 0. Let's say the position of this object was here at 0. And then maybe after, let's say, I don't know, 1, we haven't talked about measurement of time here, but let's say after 1 hour, let's say it's measured in hours. After 1 hour, let's say this is 20, let's say this is miles. So after 1 hour, this object has moved 20 miles. And then maybe after 2 hours, it's moved and now it's gone 30 miles. Total. And you keep doing this and you have some graph of this function, whatever it looks like, okay? This would be our position function. Go with me? With me? With me? If we take this function and we take its derivative, all right? So let's say we take s prime, which would be the derivative of that f function, right? What function is this? This first one is a position function. What does the derivative of a position function give you? I'm asking this like, did you see this in Cal 1?
Is it like velocity then acceleration?
It's velocity. This one is velocity. So when you take the derivative of this, you get what we call v of t, which is the velocity function. Velocity. So whatever the graph of that looks like, here it is. This is v of t. All right. Now, back to Joshua's point. If we start with our function, this was our original function. I'm going to call it here f of t, right? If we go to some arbitrary point here, t, go up to the function, the slope of the tangent line, right? The slope of that line is equal to f prime of t, which Joshua said, that's the instantaneous rate of change. Right? It's rise over run, isn't it? It's rise divided by run. This is rise over run at this one particular point. So I want to kind of illustrate something here. The derivative is rise over run. Rise is measured in what unit here? What's our up and down measured in?
Miles.
Miles. So this would be miles over, and then what's our run measured in? What's our left and right?
Hours.
Time. In this case, hours, right? So our derivative is an instantaneous rate of change that gives you an answer that's in miles per hour. And miles per hour is a velocity. It's a speed. Understand? So this function right here, this is time, okay? Time is still measured in hours. But now the y-axis is velocity. And that would be measured in what? Miles per hour. Understand? So I really want to make sure you understand this, because this is a subtle but very important point. In the original function, the x-axis is hours and the y-axis is miles, right? Hours and miles. When you look at the derivative, so when you take the derivative of this function, f prime, when you take its derivative, the y-axis is now what? What is our y-axis?
Velocity.
It's velocity, but it's miles per hour. Isn't it basically this divided by this? Right? It's this unit divided by this unit is the y-axis on our new graph. And the time still stays the same. Yes? take the derivative a second time. Okay, let's do the derivative a second time. I'm running out of room, so I'm going to do it again. I'm going to take the velocity function. So I'm going to take my original function s, and now I'm going to take derivative a second time. So I'm going to take the second derivative of the f function, which really means take the derivative of the velocity function. So if you differentiate this function, okay, differentiate it, you're going to get a new graph. This is going to be some function. And someone already said, Brandon said, this is acceleration, right? It's acceleration. So Audrey, why is it acceleration? Can you explain with what I was just explaining, like with the axes? Can you convince me that this is acceleration somehow? I can't hear you, sorry. Something. I see you unmuted yourself, but for some reason the mic doesn't seem to be working. Try it one more time. Nope, nope, don't have you. It's okay. See about, we can see about trying to get that fixed some other time. Alec, do you want to explain why, like what this would be? Alec, are you there?
Yeah, but I'm still a little confused. I'm still trying to get caught up with it. Like I
Okay,
understand.
I'm going to help you. I'm going to help you then. This y-axis,
Can I get
right,
a shot?
on this derivative, hold on this derivative, this y-axis was the y-axis here divided by the x-axis here, right? Those were the units we had?
Yes.
There you are, Alec. Okay, so if we do the derivative again, what will this y-axis units be? Won't it be this divided by this again? Like it's
Yeah,
the same
so-
format, this divided by this, so it would be what?
Would it be velocity over time or
Velocity over
how?
time.
Yeah.
Exactly, and how are we measuring velocity? Miles per hour, right?
Yes.
And then divide that by time again, you get miles per hour per hour. Miles per hour, which if you've taken a physics class is the way we measure acceleration. Right? Acceleration is measured in like feet per second squared or something like that. That feet per second squared, it's that your time unit here is always going to be squared. I'm just trying to get you to see, the main thing I'm trying to get you to see here, if you're going to take anything from this, is that anytime you have a function, whatever it is, whatever this unit is, we'll call that unit A, and call this unit B, then if you take the derivative, this y-axis will be unit A over unit B, and this will be unit B. Always. No matter what it is you're talking about. You got me? So if I say, let's say this was, let's not use time. Let's use, well, we'll use time. Let's do time. And then let's say this was measured in, well, we'll say time and we'll say in seconds, right? And let's say that this is your temperature measured in degrees, right? Like degrees Fahrenheit, something like that. Then whatever this function is, if we take its derivative, right, and graph its derivative, the units on this y-axis will be degrees Fahrenheit per second, and this will be seconds. And if you do it again, another derivative, it would be degrees per second would be your y-axis. And if you did it again, it would be degrees per second per second per second. And then your x-axis would still be seconds. Now, why am I saying this? Because Joshua asked, what does it mean to go backwards, right? What does it mean to go backwards? If we start with a function and we go backwards and do an antiderivative, what is it going to give us, right? What is it going to give us? So let's entertain that with an example. Let's say I ask you to start here, and let me say that this is time, and I tell you that this is velocity. Right? And you've got this function f here. Then if we go backwards with the antiderivative, my new units, remember this was this was velocity and time, right? What would this be backwards? Maybe I'll show you this picture. If this was, I think this picture right here, take this one. Working off of this, if I ask you to go backwards from this to here, the y-axis is going to be what here?
Would it be distance?
It would be this unit, whatever that unit is up there, right? Whatever it is,
Mhm.
could be anything, right? So in this, if we're going from here backwards, velocity is distance over time, right? So the antiderivative would give me distance here and time here, and this is position, right? So the antiderivative of velocity is position. The derivative of position is velocity, antiderivative of velocity is position. But you can generalize this, like I just said. Let's say you have, how about this one? I'm pushing here, everyone. What if this is distance and this is force?
So when you take the antiderivative, you're basically multiplying the x but with the y, and that's your y on your new graph.
You're basically, yeah, so I'm glad you noticed that. You're basically taking this and multiplying that together. See, if we multiply these two together, the unit b's cancel, and you just get unit a back here. So, okay, well, if that's what you're saying, then if this is force and this is distance, then what would this axis here be? If we did the anti. These two multiply, right? Anybody know from physics what force times distance is?
I think it's work.
It's work. It's work. And distance here. So if you can somehow calculate the force being applied on an object over some distance, the antiderivative will actually give you a way of figuring out how much work has been done. Now, I'm just loosely getting into this. So Joshua, I hope this somehow gives you some slight insight into how we can use this and what the antiderivative means. Is this satisfactory for now?
Yeah, this is definitely. I think the only other question I had was, I suppose if you have, let's see, because I know that you mentioned that distance over time was position. So if you took the antiderivative of that, would that get you? Would that get you? I guess position over time or something similar?
So yeah, things start to get weird. Okay, I mean, because if you start here and this is position, right? So let's say this is some distance and then this is some time, right? So let's say distance is measured in miles and time is measured, let's say, in hours. Then whatever that is, if you were to do the antiderivative of this, your new graph, this axis would be time, right, which would be hours. And this axis would be these two multiplied, which would be something called a mile hour, which we don't really have any good physical meaning for. Okay, we don't really have a good physical meaning for what a mile hour is. Could we do it? Yes, we can do it, but there's no meaning. There's no meaning that we can really associate to it. Just like if we start with position, take the derivative, we get velocity. We all got that. Like, we understand what velocity is. We do the derivative again, we got acceleration, right? But what if you do the derivative again?
Eventually the derivative zeroes out.
You would have something new now, right? That really doesn't have a whole lot of meaning to us. Right, so we really play within, at least within distance and time. There's really only three things we look at: position, velocity, acceleration. But if you generalize this to any graph, it kind of depends on where you start. Like, it just depends.
So not necessarily mathematically, because in mathematics you can keep on doing it even if you're just getting zero or whatever. But in a real world application, you eventually hit a point of it. There's no point going any further down third, fourth, fifth derivatives and anti all the way back up to antiderivative. You eventually hit a
Here's
point
one
of,
way to think.
that's just nonsense.
Yeah, here's one way to think about it, I guess. This might help. If you know the position of an object at every point in time, right? You have a position function. The first derivative tells you how much the position is changing at a little instantaneous point in time, right? So it gives you the speed at a point in time. Speed is the change in distance over time. Now, if you take the derivative of that, now you're going to have the change in distance over time with respect to time again. So you're saying how much does the speed change in a little instant of time, right? And that's your acceleration. If you do derivative again, then you're saying how fast is the acceleration changing over a little instantaneous rate of time.
Which even
That we
you
don't
can-
have a physical meaning for. But we could compute it. We just don't have physical meaning for it.
Yeah.
Okay, all right, we're gonna go,
Sure.
we're gonna go way off. Let me see if I can't bring us back to earth here. So in our notes.
Thanks for answering the
Oh,
question.
no, it's good. Good question. We need to entertain these things because it's important that you at least feel like you're, getting your questions answered or addressed, right? I mean, this is your education, so you're here to learn. So I'm here to try and explain things if I can. All right, so rectilinear motion, basically this means straight line motion, okay? So if we have straight line motion, we've already learned, this is what I just said, if we have a position function, that the derivative of that is velocity, and the derivative again is the acceleration. So if we're given the acceleration function, right, let's say we start with acceleration, then we should be able to go backwards to the velocity by taking the antiderivative of the acceleration. And then once we get that, we should be able to go back to the position. Let's try it. We've got 20 minutes. So let's say I tell you if the acceleration function, I'm putting a of t that is telling you it's an acceleration function. Let's say the acceleration function is negative 30t. Okay, there's your acceleration function. I ask you now to find f of t position. So I give you acceleration. I want you to find position. Now, the first thing we're going to do is we're going to find the velocity. And to do the velocity, we have to go backwards and do the antiderivative of this, which we've now learned how to do. This would be negative 30. Antiderivative of t is 1/2 t squared, right? That's what it would be. Bring in the negative 30 down. Antiderivative of this is this. But what are we going to have here? Plus c, right? The antiderivative is a family of functions. And right now, this is all I can tell you. If this is your acceleration, your velocity is one of these functions, but I can't tell you which one it is, can I? I can just tell you it belongs to this group. Now, if I want the position, f of t, I'm going to have to do the antiderivative again. You know what? Let me clean that up. That was negative 15 t squared plus c. Okay, so I just put the negative 30 and 1/2 together. So if I want to find position, right? Position now, it's got to be the antiderivative of these family members. So I can do the antiderivative of this. This is going to be negative 15 times 1/3 t cubed. That's power rule. I also have to take the antiderivative of some constant, which should be the constant times t. Think of this constant as being like the number 5. So the antiderivative of 5 would be 5t. We have to account for that. But then we have a new constant because this generates a new family. So I'm going to use a different constant d. Does that make sense?
Yes,
Questions? Brandon?
So I remember this, right?
Okay.
And if we keep going, it's just going down the alphabet, right?
Yeah, if we kept going, but we're only going to try and go from acceleration to position. So we're done at this point. Yeah. This would be our position function. So really, have we nailed down the exact position function?
No.
No, I mean, we have a family, right? There's an infinite number of these guys. We haven't nailed down exactly the one, one in particular. So what I'm going to do is I'm going to now give you a new problem where I'm going to give you some more conditions. If A of t is equal to negative 30t, and then I say, and V of 1 is, let's go 20, and F of 1, or F of 0 is 5. Now find the position. So in the first problem I gave you, all I gave you was this, and I said, go find the position. And your answer involved two things you don't know. Like there's a C and a D, and you don't know what they are. So there's this big family of functions. Here, I've given you A of t, same information, but I've also thrown on these two, what we call initial conditions or conditions. I've told you that the velocity when you plug 1 in must be 20, and the position when you plug 0 in, you must get 5. So now let's try and go backwards. If I go from here to velocity, we already did that. It was negative 15 t squared plus c. Right? We did that before. We didn't know what c was, did we? Right? We didn't know?
No, sir.
But now we do, because V of 1 has to be 20. So if I take this equation and make it V of 1 must be 20, right? That's what this says. V of 1 is what I get when I plug in 1 right here for t. So what do I get when I plug in 1 here? For t.
Negative 15 plus.
Plus c, that must equal 20, right?
Yes.
C equals
Solve
5.
for c. 35?
35, yes.
There we go. So now I know the exact velocity function. That is the precise velocity function. Instead of having the family, I've nailed down the exact one we're talking about. See the difference between the two by giving you that one condition?
Yes, sir.
Good. Now let's go backwards again. Now let's get position. So the position, we find the antiderivative of this, which should be negative. Well, we did it up here, right? We did it up here. So it should be negative 5 t cubed plus, that's the antiderivative of negative 15 t squared is negative 5 t cubed. 35, antiderivative is 35 t. But now we have, again, some constant we don't know. And I'm going to use d because I don't want to use c twice in the same problem. So I know the position within a family. And now I'm going to use this information, that f of 0 is 5. So when I plug 0 into this, what happens when you plug 0 into this?
Just zeros out and D's left alone.
All you're left with is d, good. And then the other side is 5. So d is 5. We've got our answer. Which means I can now tell you the exact position function. Plus 5, sorry. That's the answer.
That's fun.
Yeah, so
So
let me
if
show
you
you.
make an so
Go ahead. What?
no, I was just saying, so basically if you're let me see here. On C was on which one again? It was on, was it on position or velocity?
Velocity is what I use to get the c.
Okay, so if you take that function and you observe a specific position and what it equals out to, you can use that to determine C is what I'm kind of understanding.
Yeah, and this should be kind of mind-boggling in a way, Because what it's saying here is that if I know the acceleration of an object at every point in time, right? The acceleration at every point in time, then I can tell you its velocity at every point in time. All you have to provide me is the velocity at one point in time. Okay.
That's cool.
And further, if you give me the acceleration of something, right, at every point in time, you give me the velocity at one point in time, and you give me its position at one point in time, I can tell you what?
Where it is at any point in time.
Where it is at every point in time. That's, to me, that's crazy. I know everything I need to know about the acceleration, right? I know one thing about velocity and one thing about position, and I can recover the entire position function. I can tell you exactly where that object was at every point in time. That's
So I have this is kind of an odd question, but let's say you have a piece of audio, and that piece of audio has two instruments playing over it, which means that the sine wave of both instruments would be different. If they start at different times and they have different positions, you should be able to, in theory, would you be able to isolate those two audios by taking the derivative of them and finding out their position the same way you did just now?
You have two sine waves that give you so the sine wave is just the wave of the audio, right? It's the sound.
It's just the waveform of the audio,
Yeah.
right? Exactly. And let's say there's two of them. Both oscillate maybe slightly differently and at different frequencies depending on the instrument that's playing. Could you use a derivative to separate and isolate those two waveforms?
Well, you're saying derivative. We were just using the antiderivative, right, to recover.
Or I'm sorry, the antiderivative.
Yeah. I'm a little confused with your question, because we have the waveform and you're saying, can you distinguish the two waveforms or not?
You can't distinguish the two waveforms. They are a single waveform when they're combined together.
Okay, so you have the single waveform, but it's a combination of the two. And you're trying to somehow separate them out. Yes?
Right, exactly.
I misunderstood the question.
That's correct.
There's some things that you could do. I don't believe it would be this, though. It would be something different. Yeah. It would be some sort of,
I'm just curious.
Transformation. Yeah, let's talk about that different. That's a different subject.
Okay. I was just curious if this was I was trying to find an example, but okay.
Yeah, okay. So I want to try and finish this up in 8 minutes. There's one last thing that I think is just mind-blowing, okay? Do we all know the acceleration of gravity on Earth?
9.8 meters per second squared.
Okay, so 9.8 meters per second squared. This is gravity, right, on Earth. Hopefully you've seen that before. Hopefully you're okay with the idea that if you take two objects on Earth and you take air out, if you forget air, which air is there, but if you neglect the air, if you drop two objects on Earth, they will drop at the same exact rate. Whether it be a bowling ball and a feather, doesn't matter, they should drop together if there's no air, okay? If there's no air, that's what happens. When you drop any object on Earth, just let it go. The only thing acting on that, the only force acting on that object is gravity, okay? And we'll put a negative here. We'll just refer to negative as it's going down instead of up, right? So if gravity is negative 9.8 meters per second all the time, this is the measurement of the acceleration of any object that you drop on Earth. Gravitational force is a measurement of acceleration. So for any object on Earth, the acceleration function is negative 9.8. It's a constant. Gravity is constant. Now, I'm going to convert this, okay? I'm not going to use negative 9.8. I'm going to convert this to negative 32 feet per second squared. So I'm converting from meters to feet, just to make our numbers nicer, all right? If you convert acceleration of gravity from meters per second over to feet per second, the number becomes negative 32. So I'm going to use that instead. Okay. Negative 32. So on Earth, that's the acceleration function for any object dropped. Got it? Yes? All right. What would the velocity of that object be then on Earth? Take the antiderivative, right? What's the antiderivative of negative 32?
The negative 16t squared, or just t?
Yeah, negative 32t, right?
Yeah,
That's what it
oh
would be.
man, I messed that up.
Right, negative 32t plus some constant, right? We don't know what the constant is. All right. What would the position of that object be? I'm going to call it f of t. So this was our velocity. This was our acceleration. This is our position. What would the position of that object be? So take the antiderivative again.
Negative 16t squared plus ct plus d.
Plus d, right? That's what it would be. Yes? That's what it would be. Now, we have the answer of the position of that object at every point in time, but there's two things we don't know. So we have a family, don't we? We have a family. But I want to point something out to you. What is v of 0 equal to? So go to your velocity function and plug 0 in for t and tell me what you get.
Just the constant, no?
Yeah, you get c, don't you? And then I want you to tell me what f of t is. Or sorry, f of 0. What would happen if you plug in 0 into the position function? What would you get?
Just d.
Just get d, yeah.
D. Okay. Now, what does v of 0 represent? Think about this object, okay? We let it go and it starts falling, and this is the acceleration function acting on that object. What does v of 0 represent? V is the
Initial.
speed when you let it go, right?
Yeah.
This is your initial speed. And what does f of 0 represent?
The initial position.
Initial position.
Initial position. I'm running out of time. Initial position, sorry. Who cares if I misspelled it?
Couldn't technically the v also be the final speed of when it hits the ground?
Well.
Or when
V
it's
would-
not in motion anymore.
Yeah, well, let me finish because I really only have
Yep,
2 minutes.
gotcha. Yep.
So here's where we are. The position of an object as a function of time is negative 16t squared plus, you just told me that c is your initial speed, right? That's what you said c was. C was the initial speed. It's the velocity at the very beginning. In physics, we notate that with v sub 0, v naught. That's initial velocity times t plus, what about d? Well, d you said was the initial position, right? So we could call it like, I don't know, anything. Most textbooks or something will use like d naught for position. Do you all recognize that formula? Anyone take a physics class or an algebra class or something, or
Yeah,
do
that's
something with?
that's one of our kinematics equations.
going over.
Yeah, this is basically the formula, the quadratic that tells you if you drop an object on Earth, this is the formula that tells you where it is after a certain amount of time. This is the formula you use. But in order to use it, you have to know 2 things. You have to know how high you dropped it from. So this would be the height that you start at, right? The initial position. And this right here would be your initial velocity. So the question would be, did you just let it go? Did you throw it down? Did you throw it up? Okay, so if you throw it up, it's gonna take a little longer. But the main point with 30 seconds left here, the main point I'm trying to get, I guess, ingrained in your mind here is that I have a position function now, don't I? For any object that is dropped on Earth, right? I've got a position function. And the only thing I needed to know was what?
Gravity.
Gravity. Which means if I go to a different planet, right, with a different gravitational acceleration, the method for finding the position function would stay the same, wouldn't it? The only difference, let's see where does the acceleration come into play? Here it comes in, and then we get negative 32t. And then at this stage, we divided it by 2. And then here it became a negative 16, right? Like this. Everything else in the problem, all of this stuff wouldn't matter. Like nothing here is connected to the acceleration. The only thing that actually is connected to this negative 32 is the negative 16. So I can tell you this right now, that on any planet you ever go to, you know, if you take a trip to a planet, if you go anywhere, here's what I can tell you, that you're going to have some negative number sitting in front of t squared plus v naught t plus d naught. And this will be your position function on any planet. And this thing depends on the planet, right? That's the only thing that matters. So all objects on any planet fall in a manner that is governed by a quadratic function. It's always going to be quadratic. Now, as long as the gravity is constant. Okay, if your gravity is variable, then this is out the window. But okay, we made it. I think you should be able to do the homework. I think there might be 1 or 2 problems at the very end that you might have some trouble with. Just be careful when you're doing your homework. They give you a problem like this where they give you f double prime and they ask you to go back to f. That's basically exactly the problem I was just doing, except instead of acceleration and go back to position, they give you the second derivative, you go back to the first, then you go back to the original function. See how it goes. Do your best. Come to me for help. Have a good day. We're done, yes?
Thank you, Professor.
Okay.
Thank you.
All right. Have a good weekend.
Thank you, sir.
Thank you, you too.
Take care.